This slide I'm showing the voltage at the inverter terminal and the voltage at the motor terminal. You can see the voltage at the motor terminal has some spikes at twice of the DC bus voltage. That's due to reflected wave phenomena. And if you zoom in one of these spikes, you can see the waveform I'm showing on the left side, and you can see that the first overshoot of the voltage reaches to twice of the DC bus voltage. In this case was 650 volt, and their ringing frequency, or the frequency of oscillation, is close to 1 megahertz for a motor drive system when the cable length was 40 meters, running 100 horsepower. So that voltage actually makes some stress on the windings, and it can cause some leakage currents between the windings and between the winding and also frame of the motor.
Here I like to discuss how a simple magnetic circuit can be modeled. The frequency response of a simple inductor is shown here. We have two cases. Case 1, we have a coil with a core, and then case B, a coil without a magnetic core. The interesting observation here is we have the impedance versus the frequency, and the phase of the impedance versus the frequency. And you can simply see that for frequencies above 120 kilohertz, um, the core is not important. So when we reach to the very high frequencies in the range of megahertz, you remember the reflected waves was in range of 1 megahertz. So if you go above, in this case, if you go above 120 kilohertz, no matter which type of the uh, core you have, it both demonstrate the same behavior, and that's the reason that the stray capacitance is going to be dominant there, and no flux is going to penetrate at that frequency to the core. With that information, let's go to the next slide.
The two equivalent circuits represent two cases here. Case A, winding with magnetic core, and case B, winding without a magnetic core. As we can see, both magnitude and phases of the winding impedance at high frequency are the same, as we mentioned before. Accordingly, it can be concluded that the winding impedance at high frequencies would be independent of the magnetic core materials. The second observation is that the resonance bandwidth in case A is wider than the corresponding bandwidth in case B, which is the inherent impact of the magnetic core losses. In the proposed equivalent circuit, which is built around the conventional magnetic equivalent circuit, we have stray capacitance CW, RCW, and LCW. The winding resistance value, or S, as well as the magnetizing index Lm, leakage inductance LLW, and core loss equivalent resistance or core, they all can be calculated from the simple test at the rated current and frequency. The CW is the main factor there that needs to be calculated, and that is can be done by some type of finite element analysis, or it can be measured by set of tests that are presented in one of our publications. The same study as we did for a simple magnetic circuit or inductor can be done for permanent magnet and induction motors. Let's focus on the induction motor. On the left side, you can see the IEEE standard 112 model, um, which the parameters can be obtained from finite elements at the design stage or using lock rotor and no load tests when the motor is prototyped. Well, that is for low frequency, so has a stator side, magnetizing branch, and then stator side. So stator, rotor, and a magnetizing branch. On the right side, you can see distributed high frequency parameter model for stator winding. But we can see later on that rotor has no impact at high frequencies, and only the first couple of turns of the stator wind is gonna contribute at the on the motor model at high frequencies. Well, here we can see the proposed model for high frequency studies of induction machines, mainly induction motors. And as you can see, the rotor circuit and magnetizing circuit are the same as what we have in uh, low frequency model, standard one. And only we touch the stator side. And the reason is that rotor um, has no impact on the model at high frequencies. To check that, we use a small size motor, 1 horsepower induction motor. In one case, we remove the rotor. In the case we left the rotor inside, or we installed the rotor, and we measure the impedance versus frequency. As you can see on the left side, the impedance are the same at high frequency. The rotor has impact only at the low frequencies. So we touch only the stator windings, and we added CSW and CSF. These are the two main elements. CSW represent the interturn straight capacitance, and CSF represent the straight capacitance between stator windings and the frame. So at very high frequencies, only CSF is the path for the current to flow to the frame. To prove that only first couple of turns of the stator wind is going to contribute to the high frequency model. You see here we have a motor with the tap wires, and we um, have different DVDTs applied for the on the motor windings, and we measure the uh, turns voltages, and you see the voltage is going to be uniformly distributed when we have 2 microsecond type of rise time for the DVDT, I mean. But when we have faster pulses, then the stress is going to be in the first couple of turns, which would going to happen when we are dealing with, let's say, silicon carbide MOSFETs these days. In this slide, I'm showing impedance measurement of several induction motors, 5 horsepower motor, a 20 horsepower motor on the left side, and on the right, you see that 100 horsepower motor used different type of LCR meters to measure the impedances, and you can see the behaviors of all the motors going to be same. We have first resonance, second resonance, and anti-resonance point. Uh, the first resonance and of course anti-resonance points are important. Particularly anti-resonance points is the point that can cause some issues. We have a paper on that, so if people are interested, you can check that. It was a real case, a practical case that we have failure on the motor, and we were able to um, solve that issue, and then that the full report is presented in one of the papers that we had. At the end, I'm going to list the three papers that support the material of this talk today. But the point here is that um, uh, basically depends on how many number of turns you have, how the structure of the windings are, that resonance points, and the value of the impedance going to be different. Here you can compare the results of simulation of a three-phase model for induction machine running by a two-level inverter versus the measurement. You see they are pretty much look like the same, which none of the other models exist in the literature can predict the shape of the waveform as what we can do using this model.